Hello everyone, this is Alice Gao. In this video, I'm going to introduce to you supervised learning. I'll talk about the basic setting, the overall goal of supervised learning, and also what is the main challenge that we will need to address for this type of problem. Here's the basic setting of supervised learning. We are given a set of training examples, and these training examples often come in the form of tuples. So each tuple looks like this, and each tuple has two pieces of information. They're x and f of x. So x is referring to input features. And you can think about x as a vector that includes values of a bunch of features that we have about these examples. And then f of x is referring to the target features. So we are assuming that the values of the target features are generated as a function of the input features, where f is the true function that we're trying to discover here. So the goal of supervised learning is to learn a function that we usually call h, aka also known as a hypothesis, that approximates the true function f. Right, so this is the high-level goal. Remember something here. We are assuming that there is a true function f. We assume this function exists. However, when we're solving machine learning problems, we never see f. We never get to observe it. All right, so f is this hidden thing that we believe that exists, but we never get to see it. All we can do is trying to find the function h that approximates this true function. Interestingly, we can view learning as a search problem if we interpret it as follows. So we have a space of possible hypotheses, a hypothesis space or a space of possible models or representations. And our goal is to find one hypothesis in the space that best fits the data or the training examples given our assumptions. Now, often the search space we are dealing with is very, very large. Because it's too large, it's often not practical to do systematic search. As a result, a lot of machine learning techniques are often some forms of local search. So this is a really nice transition that we just talked about local search, and now we're talking about machine learning. If we're thinking about machine learning using this interpretation, then if we want to define a learning algorithm, we need to define the following three things. We need to first define the search space, the space of hypothesis that we want to consider. Then we need to define an evaluation function. So this is a function we can use to evaluate each hypothesis in our space to tell which one to compare them, which one is better, which one is worse. Finally, we need to define a search method. So given this space, which is often prohibitively large, how do we look through it to find the best hypothesis that fits the data? Let's look at a concrete example. We have a prediction task here. We have a set of points, and we assume these points are generated by an underlying true function f that we don't observe. Now we want to fit a function through these points. So which function would be the correct one? Well, let's try a few different functions. They are all some forms of polynomials. If we were to fit the simplest polynomial, which is a straight line, we may get this function, right? This line right here. But it looks like this line is not going through all of the points, and this might not look very satisfying, right? After all, we're trying to predict these points, so maybe we should try to make it go through as many points as we can. So let's try a more complicated polynomial. Here is a slightly more complicated polynomial likely a quadratic function. So this quadratic function does much better and goes through 5 of the 6 points, which is great. But there is still 1 point left that it's actually quite far from that point at the bottom, right? So can we do better if our goal is to try to fit all of the data points? Well, we can certainly do better if we go for a higher degree polynomial. So this is a higher degree polynomial, and amazingly, it goes through all of the points. So that looks pretty satisfying. If we go even further, this next function does not really look like a polynomial, but it just looks like a really complicated function that changes value a lot. But this function is similar to the previous one, that it does go through all of the data points that we have. Now I have a question for you. I've labeled the 4 functions to be a, b, c, and d. Which function do you think is the correct one? Take some time, think about this yourself, pause the video, and then keep watching for the answer. I hope you spent some time to think about this question. Now, let me discuss some of my thoughts. This is a pretty difficult question to answer, but I came up with a few ideas. The answer really depends on what kind of assumptions we're willing to make about the function. For example, if we assume that some of the data are outliers, so one prominent possible outlier is this bottom one, right? This is very likely an outlier. If we think this is an outlier, or if generally we think the data is noisy, then perhaps the simpler curves are better choices. The curves of A and B, they're better choices because they don't vary a lot. They don't pay attention to these outliers very much. Now, on the other hand, if we want a curve that goes through all of the points, then obviously C and D are better choices because they indeed go through all the points, where A and B definitely ignore this point at the bottom and maybe some other points as well. Here's another possibility. Suppose these data points are trying to predict stock market prices, but we're not getting data very frequently, so they don't look like they're very volatile. They don't look like they're changing very frequently. If that's the case, perhaps D, perhaps the last curve, the most complicated curve, is the better choice because that looks more like how stock prices change every day. So, after thinking about this question, the main message I want to get through is that there is no perfect answer to this question. All of the curves that you have seen, and maybe many other curves, can be justified as the correct one from some perspective, if we are willing to make some assumptions. This example highlights the importance of making some assumption when learning. There's a famous no free lunch theorem in machine learning, which says that in order to learn something useful, we have to make some assumptions. We have to have an inductive bias. So some examples of assumptions we can make include, do I have any outliers? Do I assume some of the data are simply not representative of the underlying function? Does the curve follow a particular parametric form? Does it have to look in a certain way? These assumptions will help learning, right? Will actually allow learning to happen. We've just seen an example, a concrete example of machine learning. Now, this example may have led you to believe that the goal of machine learning is that we're given a bunch of data points and we want to find a function that fits all of these data points well. That actually is not the case. The goal is not to predict all the training examples correctly. Instead, we want to find a hypothesis that can predict unseen examples correctly. Right? And you might be wondering, how is this possible? Well, usually the training examples and the unseen examples have some relationship. Maybe they're drawn from the same distribution. So given their relationship, we can have some hope that if we learn something from the training examples, we can use that to predict the unseen examples well. So if a hypothesis can do this, can predict unseen examples correctly, then we say that the hypothesis generalizes well. This goal makes machine learning really difficult, but also very exciting. So how do we choose a hypothesis that generalizes well? There are many techniques. I will talk about two of them. The first one is an assumption that we can make called Occam's razor. This assumption says that we should prefer the simplest hypothesis that is consistent with our data. Occam's razor is actually very useful for our daily lives. Here's a scenario. Suppose you are meeting up with a good friend who you haven't seen for a while and your friend is late. Now, if you are an anxious person, you might be imagining a lot of different scenarios in your head. Oh, what happened? Did my friend got into a car accident? Did something else? Did my friend get sick? And that's why the friend is not here. But really, most of the time, the simplest explanation is the best one. Maybe your friend left home late. Maybe there's traffic on the road. All right, so here's an example of how you can apply Occam's razor in your daily lives. Now, Occam's razor is an assumption, and it does not always work, but it tends to work pretty well most of the time. Now, Occam's razor is an assumption, and it seems like something intuitive that we can follow, but is there a more principled approach that we can use to choose a hypothesis? There definitely is, and one example of that is cross-validation. And I will talk about cross-validation in more detail in the next video. But first of all, let me mention something more important. So why is it so challenging for us to find a hypothesis that generalizes well? The reason is that we often struggle with a trade-off between the complexity of the hypothesis and how well it generalizes. There's often a trade-off between the two. If we choose a complex hypothesis, then the complex hypothesis has a lot of degrees of freedom, so it tends to fit the training data well. But sometimes it pays too much attention to the training data, so it may not fit the unseen examples well. On the other hand, if we choose a simpler hypothesis, the simpler hypothesis tends to generalize as well, predict the unseen example as well, but it usually does not fit the training data as well as a more complex hypothesis, right? So you can see there's a trade-off here. How can we find the sweet spot? How can we find the hypothesis with the right complexity such that we are confident that it generalizes well to unseen data? This trade-off is also called the bias and variance trade-off, and I'm going to talk more about it in the next video. Let me summarize. After watching this video, you should be able to do the following. Explain what is supervised learning. Explain the connection between learning and search. Explain why it is necessary to make assumptions in machine learning. Explain the overall goal of machine learning. Thank you for watching. I will see you in the next one. Bye for now.